Okay, so I'm passing around the attendance sheet, and while we're waiting for this computer to come up, are there questions on what we covered last time in terms the integrals that we covered last time and what an integral is, or anything else that we talked about? Somebody asked me after class if the material that we covered Monday and today and next Monday will be on the exam. I spoke with the dean, and it appears that the material for your next exam will be up to derivatives. The integrals that we're talking about now will be on the next exam. It won't be on the exam for this coming Wednesday. For next week, you've got an exam. All right, so it is a couple minutes after 12. We'll get started. Again, please take these out and shut them off so that we aren't disturbed. And just as a reminder, last time we talked about integrals, and we said that the integral is the antiderivative. The integral of a function is the function whose derivative is the function that you're trying to take the integral of. The integral of a function is the area under a function. And so if the function you're dealing with is relatively simple, you don't need to use calculus to figure out what the area is. In the example that we went through, the area we were looking for was the difference between a quarter circle and a square. And so you could use geometry to figure out the area under that curve. But you can't always use geometry because oftentimes those functions are too complex. But the examples we use are simple examples so that you can look at the process and not get bogged down in some complicated third order. So today I'm going to talk about integrals as they apply to statics. And I know you guys haven't had statics, so I'm going to try and keep the statics to a minimum, the technical aspect of statics. But most of these concepts are pretty straightforward. I mean, I think center of gravity is something that most people in this room will understand. The technical definition of the center of gravity is simply the point through which gravity acts. So if you were to take an object and put it at one point, where on that object would that mass act? Sometimes an ellipse. Center of gravity is right in the middle of the ellipse. If you've got a square or a rectangle, it's obvious where the center of gravity is. It's right in the middle of the square or the rectangle. But if you have an object like this, which could be, the shape of a dam, or even this could be the shape of a retaining wall or a dam, the center of gravity is not necessarily in the geometric center of that object. In some cases, the center of gravity is such that if this were, say, a retaining wall, oftentimes if you look at a retaining wall, the wall leans backwards into the soil. Well, guess where the center of gravity of that wall is? It's not even on the wall, because if you pull the soil out, the wall will collapse. So the center of gravity doesn't need to be actually on the object. But it's important to know where that center of gravity is so that when you build whatever you're building, it doesn't collapse. So where is the center of gravity? This is where it is. The center of gravity is defined by the coordinates x bar, y bar. And the coordinates x bar, y bar are defined by these two functions. It's the sum of the x coordinate and the area at that x coordinate divided by the sum of the areas for each of those x coordinates. So go back to last Monday when we looked at our example and we took the shape and we divided it into multiple rectangles. So if you were to take this, for example, divide that into multiple rectangles. Each rectangle is going to have some location. And because it's a rectangle, where's the center of gravity for a rectangle? It's in the center. So xi bar is the center of your rectangle. A is the area of that rectangle. And then the sum of all of the rectangles. The sum of the area of all of the rectangles. Similarly with the y coordinate. You're going to have a series of rectangles. Y bar is going to be the center of gravity of that rectangle. And it's going to be half of whatever the function y is. And I'll get to that in a second. So the center of gravity is located by summing the averages for the rectangles, taking the average of that area. So this is another example. In this case, we've got some function y of x that describes this curve. Maybe it's a quarter circle, maybe it's something else. The center of gravity of this area is defined by x bar, y bar. And we can find the location by solving these equations. So we can, as we did last time, inscribe a series of rectangles in here and solve this algebraically. But as we showed last time, the number of rectangles you inscribe is going to affect your answer. And if you inscribe 2 rectangles or 4 or 100 or 200 or 1,000, you're going to get a different number. The number that you get is going to keep increasing until it approaches the true area, which is defined by the integral. So we look at this differential area, dA. We'll find a differential area. And here it is. We take one rectangle. It's a differential area. Its width is dx. Its height is defined by the value of the function at the top of that rectangle. And so the centroid of the rectangle is xi, which is the center of the rectangle in the x direction, and the value of the function of y divided by 2. It's half the distance, half the height of the rectangle. So xi bar for this one rectangle is x. Yi bar is yx over 2, and ai bar is the differential area, which is simply the width dx times the height, which is y of x. So we can take these values and plug them back into the summation equations that I just showed you. So the centroid, x bar, it's the summation of xi ai, which as the number of rectangles approaches infinity, this summation approaches the integral of x dA. So the integral of x dA is equal to the integral of x times yx dx. That's dA. It's the area of this differential or elemental rectangle. The summation of the areas, as you increase the number of rectangles to infinity, the summation of those areas approaches the integral of the area, or the integral of the differential area. And the differential area is defined as the differential x times the value of the function, the height of that rectangle. So the integral of dA is equal to the integral of yx dx. What else do we know about the integral of the derivative of a? What's the integral, the derivative of a, always equal to? You almost raised your hand. It's not 0. No, it's not 1. It's a, right? Because remember, the integral is the antiderivative of the function. So if you're trying to take the integral of the derivative of a, that value is a. And so in this case, because we don't know the function y of x, we really need to go through this integration. But if we knew that this was a quarter circle, we could plug that value in right there directly and not have to go through the integration. So this is x bar, y bar. It's a similar process over here. Y bar is the sum of the y's and a's. And what is the, you take the rectangles and you increase them to infinity, and that approaches the integral. And y bar is y of x over 2. It's the middle of that differential area. And so we can pull 1/2 out of that integral, and we have the integral of y of x times the integral of dA, and the integral of dA is y of x dx. So the summation of yi bar ai is equal to 1/2 the integral of yx squared dx. And the integral of dA is also yx dx. So if we were to say, let me see if I can do this. If the value of y up here in the corner is 4, and the value of x, the maximum value of x is 2. My handwriting with a mouse is not very good. This is the origin, so that would be a 0. If the function is defined as minus x squared plus 4, with a maximum value of y equal to 4 and a maximum value of x equal to 2, we can find the actual centroid of that object by simply plugging those values into this equation. So x bar, the location in the x direction of the centroid, is the integral of x times y of x dx. So we're going to plug this into the plug these values into the integral. It's going to be the integral of x times y of x, which is minus x squared plus 4 dx. And we're going to take the integral from 0 to 2 because it's in the x direction. So we are going to integrate from 0 to 2. And then we'll divide it by the integral of from 0 to 2 of minus x squared plus 4. So this is not an easy integral to do the way it's written. So if we multiply the x through the parenthetical, it makes it a little bit easier. So now we've got the integral of minus x cubed plus 4x divided by the integral of minus x squared plus 4. Okay. So this is a pretty easy integral because you can take the integral, the integral of this parenthetical is equal to the integral of the first component plus the integral of the second component. And the integral of x to the n is simply x to the n plus 1 divided by n plus 1. So what's the integral of minus x cubed? Right, increase the exponent and then divide by it, minus x to the 4th over 4. Similarly, the integral of 4x is 4 times x squared divided by 2. And if we take that process through the denominator as well, we have the integrals are equal to this function, 1/4 x minus 1/4 x4 plus 4 times x squared over 2 divided by negative x cubed over 3 plus 4x, and we evaluate that from 0 to 2. So to evaluate it from 0 to 2, we simply plug 2 in for each value of x, and then subtract from that function the function with 0 put in for each value of x. And, and this happens a lot. When you use 0, when you plug 0 into your function, it just comes out to be 0. So this becomes a math problem, an algebra problem. Minus 2 to the 4th over 4, 4 times 2 squared over 2, and it becomes a pretty straightforward problem. So x bar is equal to 3/4. So now we know that the centroid, if this is 2, the value of 1 is probably, I'm going to guess, about here. And so the value of 3/4 is over here someplace. So the centroid is located someplace, well, that's a really lousy line, isn't it? Let me just get rid of that. The centroid is located someplace right around here, somewhere on this line. So now we need to find the value of y bar. And we go through the same process. The definition of y bar is the summation of yi bar ai divided by the summation of ai. The summation of yi bar ai is the integral of yx over 2 times dA. And so this integral becomes the 1/2 the integral of yx squared, as I said before. So now, in this case, y is equal to, goes from 0 to 4. So we take this integral, we plug in the value of y of x, which is minus x squared plus 4. And, I'm sorry, we are still going to take it from 0 to 2 because that's the direction of our rectangles. Even though y goes to 4, this is all based on an integral in the x direction. The definition of dA is y of x dx. And since we're taking the integral with respect to x, we're going to go from 0 to 2. I'll talk in a minute about the possibility of putting horizontal rectangles in instead of vertical. So again, here's your integration. In this case, multiply out this, expand this parenthetical, and when you do that, we end up with x to the 4th minus 8x squared plus 16, and it's divided by minus x squared plus 4. We'll take the integral of both of those from 0 to 2. So again, the integral of x to the 4th. What's the integral of x to the 4th? Here in the red hat. Integral of x to the 4th. So the integral of x to the n. What's the integral of x to the n? All right, so the integral of x to the n, and this is not something you can figure out. You just have to know it. You've got to memorize it. It's x to the n plus 1 divided by n plus 1. All right? Right. Yeah. And it is that simple. When x to the n, I mean, it's a really simple integration. And it's the same with the trigonometric functions. You just need to know what those integrals are or have a table that you can look them up. So this is going to become x to the 5th over 5. This will become 8x cubed over 3. 16 is, in effect, 16 times x to the 0. So that will become 16 times x divided by 1, 16x. And we evaluate that function from 0 to 2. So we do the same thing. We plug 2 in for each value of x, figure out what the function is equal to, and subtract from that the value of this function evaluated at 0, which is what I have here. And it's pretty straightforward algebra. And we come up with y is equal to 8/5. So now, well, I'm going to guess it. Let's say that's 3/4. This is 4 for the maximum value of y. So 2 is someplace around here. 1 would be about here. And 8/5 is a little bit more than half. So I'm going to call it right there. Clearly, if this were more than a simple example, you'd have to get a little bit more precise estimate of where 8/5 and 3/4 is. So the actual centroid of this object is right about here. Yes? Yes. I don't know, what was I thinking? I was thinking of 5, I guess I was thinking 5/8. So let me erase that, and if I could erase the tape, I would do that as well. But we just won't tell the dean. So 8/5 would be 1 3/5. A little bit less than 1 1/2 would be around here. What's that? Wow, this is really bad. See, what happens is after a while you get really bad at the basic stuff. So let me erase this centroid, and we'll put the centroid up here. So 8/5. So that's where the centroid is. So if, let's say you had an object that was of that shape, and you had to move that object, and the only thing you had to move that object was a 2x4, and you're going to take that 2x4 and push the object with it. Where are you going to push that object at? You're going to stand there with a 2x4 and try and push this object from here to there. Where are you going to put the 2x4? You're going to put it right here at the center of gravity, right? Because if you put it up here, what's going to happen? If you push here, it's going to tip it over. And if you push down here, it might tip it over backwards. So you're going to push at the center of gravity. So this is, that's a really basic reason why you might want to know where the center of gravity is. If this were a dam, you want to make sure you know where the center of gravity is, because there's going to be water pushing on this. And when water pushes on this, I'll show you an example in a minute, the force at the top where the water surface is very little. It's essentially 0. The force at the base is very high. It's its maximum. And so the center of gravity of the force pushing on this is not necessarily in the middle of that object. So if you're going to build a dam, you want to make sure that the center of mass or the center of gravity of your object is at least as high as the center of mass or the center of force for the water pushing on it. Okay. Questions on that, other than my failure in fractions, and I have to go back to 3rd grade? Okay. All right. So this whole previous problem was all done using vertical rectangles. You can do this same problem with horizontal rectangles. It doesn't matter. Whether you use vertical or horizontal is really going to depend on the problem itself. So in this case, we've got a triangle whose function is defined as minus h over b times x plus h. And now the center of gravity, the centroid, is located some elevation above the base and in the middle of the rectangle. So in order to solve the problem, we're going to solve this in terms of y, we've got to put this function in terms of x. The previous example, we solved the problem and integrated with respect to x because the rectangles were vertical and we were summing rectangles over from 0 to 2 across the x-axis. In this case, we're going to sum the rectangles from 0 to whatever this value is, to h. So we're going to integrate with respect to y. So therefore, we've got to find x in terms of y. And now, yi bar is equal to y. The center of mass of the rectangle is equal to its elevation, y. And the center of mass in the horizontal direction is equal to 1/2 the length of that rectangle. And the length of the rectangle is defined by g of y. So this is 0. This point is the value of x evaluated at this elevation of y. And so the area is dy, the width of the rectangle, times the height of the rectangle x, which is g of y. So we can go through the same process. The centroid in the y direction is still yi bar ai divided by the sum of the ai's. In this case, now we take the integral of y dA and y times dA, which is x times dy. This is the value of x that we got from our function, and we multiply times dy. Yes?
Where did x over 2 come from?
X over 2 is because we're dealing with a rectangle, and the centroid of the rectangle is in the middle of the rectangle. And so the elevation of the center of that rectangle is defined by y, and in the horizontal direction, the center of the rectangle is 1/2 of x. So then we know that the centroid is x over 2, but we don't know what x is until we resolve that or solve that equation. Okay? Is everybody with me at this point? Okay. And here again, we're looking at the summation of the rectangle areas, which, as the number of rectangles approaches infinity, becomes the integral of dA, and the integral of dA is a. In this case, you don't need calculus to figure out the area of this because you know it's a triangle. It's a right triangle. And the area of a right triangle is 1/2 the base times the height. We know that from geometry. So we can plug that in directly, which is basically what I just said here. So let me jump down to here. This is the equation. We're going to integrate this from 0 to h. 1/2 bh is a constant. We pull it out of the integral and get rid of the fraction. So now we're just going to integrate from 0 to h of this function and multiply the y through the parenthetical to get minus b over h times y squared plus by. Pretty straightforward integral. The integral of y squared dy, increase the exponent and divide by it. So y cubed over 3 minus b over h is a constant, so that doesn't change. The integral of y with respect to y is y squared over 2. B is a constant, that doesn't change. And now we simply evaluate this function at h and at 0 and subtract the two values. So if you plug h into here and simplify it, you end up with y bar is h over 3. So this elevation is 1/3 the height. Now in the textbook they went through an example with this in vertical rectangles, and lo and behold they found that y bar was h over 3. And if you know, in geometry, you may recall that that's the definition of the centroid of a triangle. It's h over 3. So we can do the same thing for x. Similar equations, right? The summation of xi ai divided by the summation of ai. In this case, x is equal to b over hy plus b, and dA is equal to g of y times dy. So it ends up with the integral of g of y squared and g of y squared over 2. Because x is equal to x over 2. And the integral in the denominator of g of y dy, which we previously defined as a. And we know what that is. It's 1/2 bh. Multiply out the square, and you end up with b squared over h squared y squared minus 2b squared over hy plus b squared, and take the integral of that. Again, really simple integrals. Integral of y squared is y cubed over 3. The integral of y is y squared over 2, and the integral of 1 is y. And we evaluate from 0 to h. This is the integral. This function evaluated at h is here, evaluated at 0, and you get 0. If you simplify this function, let me see where. You can simplify the function. It simplifies to this. A is equal to 1/2 b over h. Plug that in, and we end up with b over 3. So this last few steps are just algebra. So if you look at the example where they go through step by step in the textbook, they do this with vertical rectangles, and they come up with the same number. And you should. If you don't come up with the same answer, you've made an error in place. Whether you use vertical or horizontal rectangles doesn't matter. You're going to come up with the same value. So the choice is really a matter of what your problem is. What are you trying to find? And what kind of information are you given? So that's understood. We're all on board here? Yes?
So, just like, to reiterate, like, we have to remember the integral, right?
Well, you're going to have to remember, as far as I know, you're going to have to remember that the integral of x to the n is x to the n plus 1 divided by n plus 1. Or put it on your crib sheet, right? Because you're allowed a crib sheet in the exams. The same with the trigonometric functions. I don't remember what those are. I look them up. Unless you're using them every day, you're not going to remember what they are. So if you do your homework, if you're doing homework problems all the time, they might sink in. Otherwise, put them on your crib sheet. Other questions? All right. So here's another definition of the centroid that I'll show you and demonstrate its importance with an example. We talked about moments a few lectures ago and defined a moment for a beam based on flexural rigidity. And it was the second derivative of deflection. It was the derivative of the slope. Another definition of moment is a force. The moment about a point is equal to a force applied to an object times the distance between the point of interest and the point of application of the force. So for instance, if I wanted to know the moment about that point that was induced by a force applied here, the moment to the magnitude of the force that you apply times the distance between the point of interest and the point of application. So with that in mind, maybe it's intuitive and maybe it's not, but it's important in statics to analyze problems in such a way that you don't induce a moment. And we can do that because we can set the coordinates of our axes any place we want. We've been doing these examples with this as the origin, right? There's no reason for us to do that. Yes?
Is there any reason that the X and Y axis cannot have that point? They don't meet at the point?
Don't meet here?
Yeah.
That's what I'm getting to. We could, and the problem I've solved and gone over in this class so far had the origin here. But if this is the origin, and that's the center of mass, that center of mass induces a moment about the origin. Because the moment is the force, which is applied at that point, times the distance from that point to the origin. Well, it can make problems a lot easier to solve if you can solve them in such a way that there is no moment about the origin. And the way you do that is take the origin and move it from here to there. And there's no reason why we can't do that. We don't have to have the moment down here at this corner of this object, whatever this is. This could be a fan blade. There's no reason to have the there, or the origin there. We can move it right to the center of gravity of that object. And now we don't have a moment about that center of gravity, because there's no distance between the point of application of the force and the point of interest. They're applied at it's the same point. And the benefit of doing that is XdA that we've been using becomes 0. And it can make the problem a little bit easier to solve. So I put that in here. The textbook talks about it. If you find this confusing, and I know there's more elegant ways of explaining it than I just did, don't worry about it too much. The point I want you to take away from this is the origin. When we do these calculations and figure out the centroid and do other integrals in calculus, the origin, more often than not, is our choice. And an appropriate choice of origin can make the problem easier to solve. And that's something you'll get more of, certainly when you get into statics. All right. So let's look at this example. And this is a fairly real-world example. You know, it's called a retaining wall. It could be a dam. It could be Hoover Dam. It could be the dam for Lake Nakamixon or Lake Wallenpaupack or Lake Mead or Lake Powell or any lake you can imagine. It could be a retaining wall in your backyard, and instead of water, it could be soil. So there's some real solid real-world application of this. And the question is, what's the resultant force on the wall? Yeah.
May I interrupt you for just a second?
Sure.
The lab on Friday is going to be in room 216. Can you write that down, please? Sorry,
That's all right.
I'll see you there.
So, as I said earlier, if you've got a fluid and being held back by a retaining wall or a dam, the pressure on that wall varies from the surface where it's 0 to the base where it's maximum. And it's a distributed load. That's kind of hard to analyze. It's much simpler and easier if we can take that distributed load and convert it to a single point load, a resultant force. But in order to do that, we need to figure out where that force is going to be applied. And it's going to be applied at the center of gravity. So we need to figure out what the center of gravity of the force is. Well, in this case, we're going to use horizontal rectangles for our analysis. The area of that rectangle has a width of dA and a length of B, which is the length of your dam or your retaining wall. And the force, the differential force, is the function that describes the force or the pressure times dA. So dF is equal to py dA. In this case, the force is equal to rho gy, and that's a definition of hydrostatic pressure. It's the density of water times the gravitational constant times the depth. So the total force is the integral of that force over the height from 0 to h. And dF is defined as the function py times the width of the dam or the retaining wall, and we take that integral with respect to y, dy. And we integrate this rho gy b dy from 0 to h. Rho and g and b are all constants, so they get taken out of the integration. So we end up with an integral of y times dy, and the integral of y is y squared over 2. Increase the exponent and divide by it. Evaluate this from 0 to h, and the resultant force, the magnitude of that force, is rho g b h squared over 2. So that's the magnitude. So if this describes the pressure on that wall, a resultant point force has a magnitude of rho g b h squared over 2. We kind of need to know that, because if we put in a block and that block does not induce enough friction to overcome that force, the block's going to slide. So you need a mass that will induce enough friction here to withstand that resultant force. And it has to be built in such a way that its center of mass will not be significantly lower than the location of that resultant force, because otherwise it's liable to tip over. So here we're using integrals to figure out how to build this wall and how much water you can hold behind it. So this point goes back to this idea that you don't always have to use calculus. Sometimes, if it's a simple function, you can figure the answer out without calculus. The force that you're given is clearly induces a triangle, and it's a right triangle. And the area of that right triangle is 1/2 the base times the height times the length of the wall. The area that that force is applied over. You don't need integration to figure that out. So we can simply take the length of the wall times the area of the curve, which is 1/2 the base, which is rho gh, times h. So you don't always need integration, but you need to understand the process so that when the function is not inducing a triangular or rectangular force, you can still solve the problem and you're not stuck. Questions on this? Real quick example. All right. One last example. Again, this is right out of your textbook, so hopefully it's not completely new to you. In this case, we have a distributed load that's defined as Wx. It clearly is not a triangular load. We're never going to figure out the area under that curve without integration. The question is, if this is the distributed load, what's the magnitude of an equivalent point load? And where is that equivalent point load located? By definition, and again, this is not necessarily something that anybody expects you to figure out, but to solve this problem, you need to understand this. If it's statically equivalent, then by definition the moment of each load has to be the same. The moment of about each point has to be the same. So if we go back here, the moment induced by this distributed load at this point has to be the same as the moment induced by this point load at that point. And the moment induced by the distributed load at that point has to be the same as the moment induced by the point load at this point. So if the two moments are equal, we can set them equal to each other and then solve it. And again, by definition, the moment is equal to the force times the distance between the point of application and the point of interest. And we're going to define the point of interest as the origin, and the origin is located here. So the moment induced by this distributed load is equal to the distance times the load at any given point. And so we integrate this from 0 to L, that function, and multiply it times x in order to find the moment induced by that load, by that distributed load. For the point load, it's a little bit simpler. The point load is simply equal to the value or the magnitude of that point load times its distance. And the magnitude of that point load is equal to the magnitude of the distributed load, which is the integral of the load dx, wx dx. So if we set these two values equal to each other, we can solve for L and figure out where that resultant force is located. And we can also solve for R. So in this case, we set them equal to each other. The integral of x dw is equal to RL. RL is equal to L times the integral of wx dx. And x dw is equal to the integral of x wx dx. And they're both integrated from 0 to L. So L is simply equal to x wx dx over wx dx. Does that look familiar to anybody? It's the definition of the centroid. A couple of slides ago, I showed you that the centroid is defined as that integration. That's what this is, except this is expressed in terms of y of x, and this is expressed in terms of w of x. It's the same thing. So by definition, a resultant point load is always located at the centroid of the object. And if you know if you can figure out where the centroid is, then you know where that point load is going to be applied. So then you just need to figure out the centroid. Whoop. There we go. So I'm just about out of time. This is in your textbook, so I'm going to go through it real quick. In this case, again, it's a simple function. It's W naught over L times X. It induces a triangular load. What's the area of that triangular load? What's the...
Half base times height?
Right, it's 1/2 L times W naught. Where's the centroid of that load, that distributed load? For a triangle. It's not in the middle. It's h over 3. And in this case, h is equal to L. And let me rephrase that. H over 3, but from the bottom, from the base of your triangle. So it's 1/3 the distance from here. And that's what they're going to show you in that calculation. The magnitude of the resultant force is simply the area under that curve. It's 1/2 W naught L, and you can do that without integration. But knowing how to integrate this is going to help you when you get some more complex integrals that you can't just solve geometrically. So we solve this integral, and we come up with 1/2 W naught L under the distributed load. That's the integration. That's the magnitude. The location given by the location of the resultant force is defined by the centroid And if we go through this math and the integration here, we'll show that, in fact, the centroid, in this case, 2/3 L. Well, it's 2/3 measured from here, right? Which is going to take you 1/3 of the distance from here. And then you can go through the rest in terms of, the rest of that problem has no calculus, it's just algebra. So I'm going to, on Monday, talk about integrals in dynamics. If you've got questions on this stuff, bring them on Monday and I will try to address them then. Otherwise, I'm going to continue into dynamics. I know I went through this pretty quickly today. So again, if you've got questions, bring them on Monday and I'll try and answer them, and then we'll continue into dynamics. Oh, and the sign-in sheet, who has it?